Hi everyone. In this lecture you guys are going to learn about lighting systems design. Throughout this lecture you will learn about what is lighting, what are the characteristics and properties of light, and you will learn how to do a proper lighting system design for a indoor area. When it comes to light and vision, these are few things you might already know. You know, light enables us to see the world, right? So without light you can't do anything. And human eye can see the color, brightness and the contrast of surfaces, so not objects. Objects are determined by the brain after processing the signals coming out of your eye. And if you consider colors are just sensations felt by the eye. It is a property of wavelength that enters the eye. Actually there is no relationship between wavelength and the colors. The colors are defined by your brain considering the signals coming from your cells inside your eye. In here we are going to talk about the brightness. The amount of light reflected or released from a surface is called the brightness, and this brightness allows you to see the details of a surface. Okay. Contrast is defined as the difference between brightness levels of objects within the same field of view, or in simpler word, the visual difference between bright and darker areas in a surface or picture. So this contrast allows us to recognize the edges of the image. Observe the images I have given in this lecture slide. The first one is a low contrast one. In the low contrast one, you can see the brightnesses of all the surfaces are not very different, right? So the baby's hand and the chair, they almost have the same brightness. If you come to the second image, you can easily identify the surfaces. See, the brightness is different in each surface. So this is a balanced contrast. So this is the one we should have in an image. And in the third image, it has very high contrast. The edges are very sharp. See, when you have a very high contrast, the lighter areas get very white and the darker areas get very black. So the image is not very clear. So the best practice is having a balanced contrast. In here I have included the electromagnetic spectrum we can observe in our world. So this electromagnetic energy is propagated as radiant energy, so we call them electromagnetic radiation. So these in these electromagnetic radiations you can observe the energy they contain by using the equation E equals HF. So it is measured in watts, and within this range we have a small region called visible spectrum. This is where our light is at. So we can observe these wavelengths using our eye. So this range normally start from 380 nanometers to, and it goes up to 740 nanometers. And these, so it contains a range of wavelengths. These wavelengths are sensed by our eyes as colors. Okay, here we are going to talk about light. In earlier slide I explained to you about the visible spectrum. The light is located in the visible spectrum. So the definition of light is given as the visually evaluated radiant energy. In this definition, this visually evaluated term is very important. So now we are going to talk about why this light is visually evaluated. So In the previous lecture slide, I told you this energy is measured in watts, but our eye sensitivity acts little bit differently. So if you take two LEDs, one is 1 watt green and another one is 1 watt red, our eye will see 1 watt green LED much brighter than the 1 watt red LED. So that means our eye has different efficiency levels for different wavelengths. So therefore this light cannot be evaluated in terms of watts. So we need to have a different method to evaluate light. So we are going to talk about in later slides. In this lecture slide, we are going to talk about standard photometric observer. This is the same thing I explained before. This photometric standard observer defines the efficiency levels of our eye sensitivity. So if you observe closely, our eye has the highest efficiency at around 540 to 560 nanometers. So this standard photometric observer values are used when you calculate the lumen values. In this lecture slide, we are going to talk about luminous flux. As I mentioned before, this light is visually evaluated, so we can't use watts as the unit to measure the light. So a separate unit is introduced to measure the light. It is called the lumen. There's a simple definition for lumen. It says 1 watt monochromatic light at 540 terahertz or 555 nanometers wavelength will have a luminous flux of 683 lumens. In here, this monochromatic term is very important. Monochromatic means that light does not radiate at any other frequencies. It only has the fixed frequency, which is 540 terahertz. Now we are going to talk about the illuminance. Illuminance is the lighting level of a surface. It is defined as luminous flux per unit area. This is measured in lux. The definition of lux is given as a single lumen or one lumen falling perpendicular to a unit area. That means a 1 meter square area will create an illuminance of 1 lux. I have also given the equation. The illuminance is equal to luminous flux perpendicular to an area divided by the area. In this lecture slide, I have given some typical illuminance levels in our surroundings. So looking at these values, you can get an idea about this lux unit. So I have given some situations. If you consider sunlight has a lux value of around 100,000. Moonlight will have something around 0.1 lux, and starlight will have 0.001 lux, and office areas will usually have 300 to 500 lux, and corridors are normally designed to 100 lux. Here we are going to talk about various lamp types available. Following are the most common lamp types available in installation and where those lamp types are especially used. So you all know fluorescent lamps, right? There are two types, the tube type and the compact type. Mostly these things are used in homes and offices. And we have halogen lamps. Halogen lamps are mostly common in automobiles. As headlamps, halogen lamps are used. Then we have high pressure sodium vapor lamps. These lamps are used in warehouses and shipping areas. And next we come to low pressure sodium vapor lamps. These are the lamps we see in street lighting. So if you see amber color street lights, those are low pressure sodium vapor lamps. And LED lamps, we all know, we use them in our homes. And metal halide lamps, these are the lamps we use in large sport arenas. Then we come to incandescent lamps. These are the lamps we used in like few decades ago in our houses. Still they are available, very cheap, and but not very efficient. Now we come to the luminous efficacy. Luminous efficacy is a measure that we take to evaluate how well a lamp performs. This is the ratio of luminous flux to the power. So it is measured in lumens per watt. So I have given some lamp types and their luminous efficacies. You can see the fluorescent lamps can go up to around 104 lumens per watt, and halogen lamps 35 lumens per watt, and high pressure sodium 115 lumens per watt, and you all know LED lamps 120. And the highest value you see here is the low pressure sodium vapor lamps, which has 200 lumens per watt, which is a very good luminous efficacy. But the only drawback is these lamps come in only one color, the amber color. That is not very suitable for most applications. That's why those lamps are only used for street lighting. Next, I have added a video clip in this lecture that will get you an idea about these uncommon lamp types we talked about. So it will talk about these halogen, high pressure sodium vapor, and the metal halide lamps. Those things are not very common in usual installations. So take a look at that. Then after that video clip, we are going to talk about how an indoor lighting system is designed.
All right, so the next type of lamp that we're going to talk about is the metal halide lamp. So metal halide is from the HID family. HID lighting means high intensity discharge. Essentially, these work very similarly to a fluorescent lamp. You're sending an arc through a tube. That tube has a certain gas in it that's able to produce a really high intensity arc, and through controlling the substances that are inside of that tube, you can control the color and the temperature of that tube. So essentially how an HID probe start bulb works is you've got electrodes, one on each side. Those electrodes are essentially just filaments, and then you have a starting probe as well, and that starting probe has a starting resistor. But when current starts to go through this lamp, basically inside of the bottom of it you have this little arc that happens, and that arc will ignite the argon gas that's on the inside of this, and it starts to heat up to a point where there's a small trace amount of mercury inside of here, just like a fluorescent bulb would have. But that mercury starts to vaporize and create an arc all the way across this tube from one electrode to the other electrode. And it's a really low blue color, so you'll notice when these first start to turn on that it's just this low, barely an arc at all. It just looks like a stream of low blue light, and that's the mercury. That's the color that mercury burns. Now in the inside of this tube, you have this cloudy kind of film all the way around that inner quartz tube. What that is halide salts. These are called metal halide lamps. So halide salts are certain chemicals that when vaporized, they will start to kind of change color. So instead of like a fluorescent lamp relying on phosphorus to get its luminescence from, the arc alone inside of here is bright enough to strike a light, but they want to kind of control the color output so that it produces a certain amount of light and a certain spectrum of light, really. So these burn at about 4000 K, which is a pretty white color. But those halide salts that are on the inside of this each have kind of their own color profile. So once each one of those halide salts vaporizes and gets entered into that same arc stream that's inside of here, it changes the color of that arc. and it goes from that low blue to kind of like a pinkish and then a purplish, and then it all of a sudden dissolves into white, like really brilliant white light. And that's when all of the halide salts are evenly burning. So another note on that, if you notice, most metal halide lamps have this white paint at the top and the bottom of each one of these quartz tubes. Reason for that is that white reflects light. So that's like when you're in the summer, if you're wearing black, you know, you're going to be really hot, but if you're wearing light, a lot of that gets reflected off of you. So the reason that that needs to happen is that some of those halide salts inside of here have to maintain a certain temperature. And if they get down below a certain temperature, you'll see the color start to shift inside of the lamp, and it becomes really unstable, and it just color shifts a lot. So for the color to stay a stable white, you need to maintain a certain temperature inside of there. So what it does is all of the heat that comes off of this lamp, about 25% of it will go back into the lamp to maintain the temperature of the arc. 75% of it is wasted as heat, but another 25%, when you paint the white, it reflects it back into the tube, so that that amount of heat is able to stay in the tube and stabilize the color of that arc without it shifting on you. Every one of these bulbs is going to have a mounting position in them. So like this one says U, it says 1000 watts / U. So U means universal. It means you can mount it upside down, you can mount it sideways, upward, doesn't matter. The arc is going to act the same way in that tube regardless of how the thing is mounted. There are some things that are meant for mounting upside down or base up. And the reason to that is if you strike an arc in there and you were to turn the lamp sideways, the arc would dip because of gravity. It's going to dip in the middle, and it's going to be arcing against the side of that inner quartz tube, and it's going to heat that quartz tube up to a point where it's going to weaken it, and eventually it's going to burn out or have like an explosive death. A lot of these tubes get so hot that they will blow up. And so you got to make sure the mounting position on all the lamps that you're getting is specific to its purpose, or that it's universal, meaning that the lamp's designed to be used in any way because of the characteristics of how they designed it. It can handle that. Next up on our list is the high pressure sodium lamp. So high pressure sodium is another type of high intensity discharge, much like the metal halide, but you can tell that the arc tubes are completely different. So a high pressure sodium has a lot skinnier type of tube, and you can tell that that tube is not clear. It's not actually made out of glass or quartz. And the reason being is with sodium and mercury on the inside of this thing, you have to have such a high amount of heat that glass or quartz would just break. So what they did is they came up with this specific type of ceramic. It's like alumina oxide ceramic, and that is what that whole tube is made out of. Now the base gas, rather than it being argon in this tube, the base gas that arc has to go through is actually xenon gas. And so it operates very similarly to any of the other HIDs, but what makes it different is you have to send a high voltage pulse through this to be able to ignite an arc to get through this material. The inner tube is filled with xenon instead of argon, like a lot of incandescent and fluorescent lights, but that xenon is what the initial arc is stabilized through. And then there's mercury inside, just like almost all these other gas type fixtures. But there's also sodium. So sodium burns at like a really yellow color, especially like the low pressure sodiums before these high pressure sodiums came out. And the mercury also has like a bluish color to it. So when you mix the two of those together, you actually get this kind of like golden orangish white color. And the advantage of that is a low pressure sodium lamp or any other just regular type of sodium lamp puts off a really yellow light, and it makes everything around look extremely yellow. But mixing mercury with that blue spectrum and the sodium with that yellow spectrum, when you mix them together, you get kind of a whiting effect that allows for yellow light to be around, but you can still tell the color of the things that you're looking at. Not everything just looks yellow. It's yellow light, but you can still tell the color of everything around you. So that's the purpose of this lamp. So the process for how this works is the ballast outside of here actually has an igniter. A normal metal halide fixture is not going to have an igniter to it. That's how you can tell the difference between the two ballasts when you're looking at them. That igniter, once current is run through it, sends a high voltage pulse of current through the lamp to strike an arc. So that tube inside of here, the base the base gas that's inside of the tube is xenon, and then there's two other types of gases that are created once the heat inside of the tube rises. The first one is mercury, just like all these other types of lamps. That mercury gets to a certain temperature and it starts to vaporize into that arc stream, and the sodium does the same thing, but the mercury is a little bit lower temperature when it burns, so it burns first. And then once it gets up to a certain heat level, then the sodium starts to burn. So you'll start to see when this thing ignites that you've got this like baby blue color once that mercury starts to ignite. And then once the sodium starts to ignite, you'll start to see it's shifting colors to much more of a yellow color. These bulbs get very, very hot to the touch. So I mean, like, you could melt your skin because it's like, depending on the wattage of the lamp, the size of the envelope, everything, and whether or not it's mercury vapor, metal halide, or high pressure sodium, they can get anywhere from like 400 degrees Fahrenheit to 800 degrees Fahrenheit to the touch. So just be really careful working on these. High pressure sodium, you can tell when the lamps are starting to fail because they cycle on and off. So you'll see if you stand in a parking lot for 30 minutes and just sit and watch one of these lamps, it'll shut off and it'll be off for like, I don't know, 10, 15 minutes, and then it'll start to ignite again, and it'll get up to pretty close to full bright, and it might even stay there for a minute or two, and then it shuts off again. And it just keeps doing that over and over and over, where a metal halide's not going to do that. So that's how you can diagnose whether or not a high pressure sodium lamp is your problem. So the next type of lamp I'm going to talk about is another bulb that's in the HID family. So this is the mercury vapor lamp. So all three of metal halide, high pressure sodium, and mercury vapor all utilize mercury inside of them. That's really the only thing that they have in common, except for the fact that they're igniting an arc through a gas. What's unique about the mercury vapor, though, is it only needs that mercury in the tube to produce light. The other ones, high pressure sodium, it's utilizing mercury and sodium, and the gas that's inside of it is xenon rather than argon. This just has a little bit of argon in the central tube, and then it has a little bit of mercury in it. So you still send this with a pulse, and you ignite an arc from the bottom electrode to the top electrode, and once that argon gas and that arc get hot enough, it starts to vaporize the mercury inside of it, which lets off a blue light. But everything stops there. It's just a blue light, it's just mercury, that arc, and that's it. So you'll see a lot of the clear mercury vapor, not the ones that have a phosphor coating like this, but a lot of the clear ones will burn like a hyper blue light, and they're like 6500 K on the spectrum, so really, really blue. What they've done with a lot of these other ones is to still kind of get a white light out of it, something that's back more in the like 4000 K color, is they put phosphor around the inside of this just like they would on a fluorescent lamp. And what that does is it mixes that blue light with a little bit of white. Again, the mercury on the inside of that tube is producing UV light, and when you shine UV light on phosphor, it makes the phosphor glow, so it gives it almost a fluorescent kind of feel, but it's a different spectrum of light. So you can't see this here, and unfortunately I don't have a clear mercury vapor lamp, but if I did, what you would see is essentially this exact same thing. It's going to look like a high pressure or a metal halide lamp, but you're not going to have the white coating that's painted on the tops of that quartz tube because it's not necessary. Remember, the only reason that that white coating is there is because some of the halide salts for the metal halide light specifically have to have that coating so that it maintains the arc and those colors don't start fluctuating, because those specific halide salts have to have that white coating. So on a mercury vapor that's clear, it's just going to be a clear tube, and that's it. There's no need to have anything else. It's just mercury burning through it, and you want that blue light.
Okay, from this point onward, we are going to talk about lighting system designing, and you guys need to know in BS 7671 it does not cover the lighting system designing. We have to refer to the CIB-SC lighting code, or also known as Chartered Institution of Building Services Engineers lighting code. So that is the document we are going to refer in this section. And when you are going through this section, you are going to learn about what are the key things we need to consider, what are the lumens levels for each applications, and how to use lumen methods to do a complete indoor lighting system. We are only going to cover the indoor lighting systems in this section under the bachelor's degree level, and that is the most important part in lighting system designs. And these are the key points we need to consider about when you are doing a lighting system design. First of all, you need to make sure about the safety of the occupants. Then you have to make sure that occupants inside the building can carry out their task effectively with your lighting system. And you also have to consider about the appearance of the interior. Maybe some lighting conditions may not be applicable or approvable for some applications. And also you have to consider about the initial cost and operating cost, and you have to do a cost effective design, and you also need to do a energy efficient design when it comes to lighting. In here we are going to talk about one of the most important things you have to consider when you are doing a lighting system design, the safety of the occupants. When you are doing a design, you have to avoid deep shadows. So these deep shadows can hide obstacles, so that can harm the occupants. And the second thing is, you also have to avoid the glare. Glare is the reflection from a surface due to a distance light source. So this glare can also affect the vision of people, so that can also do harm. So you have to avoid the glare. And the next thing is, you have to avoid the stroboscopic effect. So if you have synchronous machinery in a place and you have synchronous light bulbs, that means the light bulbs turning on and off depending on the AC waveform, most likely incandescent light. So there can be a effect called stroboscopic effect. So when there's stroboscopic effect, these machines can appear as stationary, but actually they are rotating. So this is a effect due to the light source. So you have to avoid putting those specific light sources in these kind of areas. In here we are going to talk about task lighting. Earlier I mentioned that designer should do the design where that users of the interior can carry out their task effectively. So to carry out the task effectively, the CIBSC code has given some recommended illuminance levels. So this table contains those illuminance levels. So if you observe the table, you can see they recommend 300 to 500 lux for general offices and computer workstations, and shops 300 to 500, supermarkets 500 to 1000. And if I ask you to do a lighting design, you have to refer to this table and select the illuminance level and start doing the lighting design. Okay. Now we come to the economy and energy efficiency. So when you are doing a design, you have to do that design economically. So you should not over design your lighting system. You have to have the adequate lighting levels but not excessive levels, and you have to make sure you are using the most efficient light source available, and that should be suitable for the task also. There are some light sources, those are not suitable for some task, so you have to avoid those things and use the most efficient and the most suitable light source. And you have to use the most efficient luminaires. We are going to talk about what are the luminaires, and this is a important thing. So you have to make sure that surfaces of the room, that means walls, ceiling and the floor, are light colored. So if those things are light colored, they reflect the light very well. So you can choose a low power rated light bulbs to get the same illuminance levels. And you have to make sure that you can utilize minimum amount of luminaires to achieve the target illuminance, and you can have controls to dim the light bulbs and all. Those things are also economical, and you have to establish an proper maintenance program. That is very important. Another thing to mention is energy conservation of lighting system designs. Now according to the regulation, they require energy efficient lamps to be used in lighting systems to make sure there's energy conservation, and designers should have controls to use daylight conjunction with the electric lighting. So you can dim the lighting when you have sufficient daylight coming into the building. And now we are going to talk about luminaires or lighting fixtures. Luminaires are the enclosures of lights we have fixed to our ceilings. I think you all have seen these types. There are many types available, but these are the most common ones. So in slit we have these recessed mount fluorescent fixtures. Now we come to the lumen method. This is the main equation you are going to use in lighting design. This equation is for average illuminance level. So when you have the lamp fixture type and how many lamps available, you can calculate the average illuminance. But we already know this value. Remember, earlier in task lighting, the CIBSE have specified illuminance values for all the applications. So in this equation we know this value. What we don't know is these N and capital N values. So these are the number of lamps per luminaire and number of luminaires. Number of lamps per luminaire you can select. In this calculation, mainly you are going to calculate the number of luminaires for that room. Other factors, utilization factor, maintenance factor, those things you can calculate. Mostly they will be given. Area you can calculate very easily. And the initial bare lamp luminous flux, the F value, it is a property of the lamp you are going to select. That value is given in the lamp catalog. And here you can see initial bare lamp luminous flux values given for Philips T5 lamps. T5 lamps are fluorescent lamps. So in the catalog they have mentioned the approximate initial lumens. When you are doing your calculations, you have to refer to the catalog and find out this value and use it in the equation. Now we come to the utilization factor. In a room, ceiling, wall and floor surfaces are reflective. So those reflected light will affect the total flux received on the surface. So we have introduced a factor to evaluate that, called utilization factor, that is the ratio of total flux received by a surface to the total lamp flux of the installation. So when you are calculating this utilization factor, you need to know two things. the room index and the reflectance values. Reflectance values are, you need to find out these values using equipments, and the room index you can calculate easily. So if you observe this figure, you can see the luminaire plane, the horizontal reference plane. So these two planes play a major role when you are calculating the room index. So the room index equation is room length into room width divided by room length plus room width and the difference between luminaire plane and the horizontal reference plane. So if you have recessed lamps, this luminaire plane is also equal to your room height. Horizontal reference plane is the working plane. Usually it is the height of a table in the room. Room reflectance. Room reflectance is defined for ceilings, walls and floors separately. So in here I have given example. If your ceiling is 70% reflective and the wall is 50% reflective, floor is 20% reflective, your room reflectance will be 70, 50, 20 CWF. That will be your room reflectance. After finding the room index and the room reflectances, you can easily select the utilization factor from this table. So if you take a simple example, if your room reflectance values are 70, 50, 20 and your room index is 1.25, your utilization factor will be 0.75. But many cases your room index will be something like this. So if you have a room index of 1.87, you will have to do a simple calculation like this and find out the utilization factor. Maintenance factor. Maintenance factor is defined for environmental conditions. So if you have a clean environment, your maintenance factor will be 0.9. Average environment 0.8, dirty 0.7. That is the everything you need to know when you are doing a indoor lighting system design. I will upload a tutorial, and in that tutorial I will discuss how we can do a indoor lighting design with example.